Yeah. So also the videos will be recorded, and you can see the recordings immediately after the sessions. I usually upload within half an hour. It takes time for the processing. So within half an hour, the videos will be uploaded. Whereas the slides are already up for this week. I'll upload right away at the class, but usually I try to upload it before the session itself onto the Google Drive. Okay, so in this week, week 7, professor has discussed about new type of architectures called as recurrent neural networks. So we slightly shift from the typical CNN architectures which we were discussing till now. We discussed a bunch of CNN architectures like ResNet, ConvexNet, and we also discussed about architectures like faster RCN and YOLO and all. But those are all inherently using convolution operations. Now, in this week, we shift slightly towards how do we handle when the data is sequential in nature, and that is where this concepts of recurrent neural networks, then LSTMs, GRUs, and how can you do use those architectures for data when your data type is video, because video is nothing but a sequence of frames. So let's go ahead with the questions. So we'll start off with a very simple question. So we have two sets, and you have to match which is the most appropriate matching. Like what is the correct task for many to one, many to many, and one to one. So you can just drop in your answers in the chat, and I'll just wait for a minute. Yeah, maybe let me discuss then, because it's very simple thing. So let's look at it. Yeah, yeah, sure, sure. Go ahead.
Machine translation is many to many.
Mhm.
Scientific classification is many to one. And music generation is one to many.
Yeah, you are correct. So let me show the answer for everyone. So one to many is music generation, many to one is sentiment, many to many is machine translation. So let's look at the tasks itself first. What is music generation? So you can think about your music generation like your LLMs, right? For your chat GPT, you give a prompt and it should generate an answer. Instead of answer, you're generating a music. So your prompts are usually a single prompt, like make a classical song, or simple prompt. And music generation is an entire sequence of notes, right? A song is sequence of different notes and chords and everything. So that is why it is going from one input to many out. Now let's go to the second task, which is sentiment classification. So what does sentiment classification say? Given a particular sentence or a paragraph, what is the sentiment behind that? Usually we talk about positive and negative sentiment in terms of movie reviews. So you all are familiar with movie reviews, right? People say whether they like the movie or the movie is bad. So you this is a very popular task for where you have a bunch of movie reviews from IMDb, which is a website that do movie reviews. So you collect that data set, and then you train your model to look at the review and tell whether it's a positive review or a negative review. So here the input is an entire bunch of words or sentences or characters, and the output is just a positive or a negative class. So that is why this is a many to one. Now let's come to machine translation. I think everyone is aware of the task itself. It basically translates from one language to another language, like English to French, English to Hindi, Hindi to English, etc. So obviously here the input will be multiple sentences, and the output obviously will also be multiple sentences in a different language. So that is why machine translation is a many to many. So I hope this is clear. I'll just move on to the next question. If there's any doubts, you can always unmute and ask me. Now let's go into a little bit about the RNN architecture itself. So what do you think are problems with associated with your traditional recurrent neural networks? So these are all the options. Just select. Is there a question? Yeah.
One answer is one.
No, that's not the correct answer. Yeah, I think someone answered in the chat.
Four.
Uh, Yeah, four, all of the above. So all of the above are problem for recurrent neural networks. So let's discuss it. So one is obviously, I think that is the most evident problem which all of you are aware, vanishing and exploding gradients problem. Where, but I'll still explain. Vanishing gradient is nothing but during your back propagation. What do we do in back propagation? You keep sending gradients from the last layer, uh, output layer to input layer. So you keep on sending the gradients one layer after the other by multiplying some values. Vanishing gradient talks about when in this process of sending the gradients backward, there will be a point when the gradients become so small that it is almost equal to zero. And all the layers which receive the zero gradient will not get any update done, because it will feel like, okay, there is no change needs to be done to the weights because it is giving correct answer. So that is a problematic thing that you usually encounter with RNNs. Exploding gradient is the opposite. When these gradients are very large, and when you multiply two large numbers, they become even larger. So that is how the at some point the gradients just becomes almost infinite value, and your model just crashes. So that is another problem which you encounter with your traditional RNNs. So one is the correct answer. Second option talks about problems in dealing with long-term dependencies. This is actually true. So if you use your algorithms, RNN algorithms on very huge sentences or paragraphs of any document, right? After a point, it won't remember what it has seen on the starting sentence or the first few words. So this is a big problem with RNNs, and this is actually one of the motivations why transformers or attention worked better, because it helped in dealing with these long-term dependencies easily. Attention started, then people moved on to transformers, which uses a type of attention. So that is why point number two is also correct, that long-term dependencies is problem in traditional RNNs. Again, point number three says processing the data sequentially. This is again true, because if you look at the traditional RNNs, what do? We have a hidden state from time t minus 1, and that goes as an input to the current time step t, which further goes as an input to the next time step t plus 1. So there is a dependency at every time step, there is a dependency on the previous time step. So this is nothing but sequentially you're uh, dealing with the data, right? Or your model is sequentially analyzing the data, processing the data. So this is again problematic, and this is one of the motivations again for transformers, which you will be discussing in week 8. The lectures have already been uploaded. That transformers deal the data or process the data parallelly. They don't do it sequentially with this hidden time step t minus 1 to t and t plus 1. So that is why problem point number 3 is also a problem for traditional RNNs. So 1, 2, 3 are the correct answers. So the correct answer is all of the above. Okay, is it clear, or are there any questions to related to any option? Okay, great. So let's move on.
Excuse me, can you discuss one to vanishing? I didn't get that.
Okay, so vanishing gradient, the concept basically says that if you have 10 layers and you have 10 layer model and a 50 layer model, these are model A and model B, let's just go. So in 10 layer model, what does backpropagation do? You calculate loss after the 10th layer, and then you start sending your gradients back from 10, 9, 8 up to first layer. Now, what happens is when you have a larger architecture, or for that reasons, when you, in our case, it is cross time, right? Because if you have longer dependencies of time, you'll have a larger, what is a flow of time to go back to. So when you have these long sequences that you have to travel back, the gradients are values between 0 and 1. So two small values multiplied with each other gives even smaller values. So in that way, the values keep on decreasing, 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 and at some point it will become close to 0. And every layer which receives a 0 gradient, right? All of them will think, okay, I don't have to update my weights anymore because I'm not getting any gradient. Gradient is the reason why the weights are updated, right? If you're not getting any gradient, it means that I don't have to update. But that is not true. The problem over here is the vanishing gradient. It's not that the model is doing good. So that is why it is a problematic thing in traditional RNNs. Is that clear?
Yeah, got it.
Yes. Let's move on to the question 3. So in LSTMs, long short-term memory networks, we have three different gates called the forget gate, input gate, and output gate. And the equations are shown in the bottom. Like forget gate takes sigmoid of weights WF with the current time step xt plus UF is the matrix which multiplied with the previous time hidden state HT minus 1 and the bias term. Similarly, you have for other gates IT and OT. So given this equations and the functionalities which professor has discussed about these three gates, match the 3 1 2 3 to the correct uh, mechanism that they follow in ABC. I'll just quickly pause for a second, just answer it in the chat.
One C.
Okay. Try to answer all of them. All of them have to be matched.
Okay. One C, two A, three B.
And no, it's let's just wait for everyone.
1C, 2B, 3A.
Yes, that is correct. So the correct answer is 1C, 2B, 3A. Let's just discuss it. So what does forget gate do? The functionality of forget gate is basically trying to decide how much from the previous state the data should be forgotten. So or how much it should be forgotten or how much it should be kept. It's vice versa basically. So that is what the functionality of forget gate is. That's what this state decides how much from our old cell state the data should be kept. Now let's come to the output gate. That's easier to answer. Output gate, like the name suggests itself, it just controls on what should be the amount of information that should go to the next hidden state, or control on the output, because amount of information is nothing but the output. So that is the closest answer is A, controls the output to the next hidden state. What does input gate say? Input gate says is, okay, now I have some previous information, now I have some new information. How do you decide which out of these two should I store in my current cell? Like which should be given priority? Is it a hybrid or one should be neglected and all? Those all information will be decided by the input gate. So 2 is B. So these are the answers 1C, 2B, 3A. So the same thing, you can also look at the equations and you'll understand that the operations are happening in a similar. Moving on. Question number 4, it's a bit lengthier question. So there are functional, structural and gating differences between these two architectures, long short-term memories and GRUs, gated recurrent units. So each question has a bunch of different differences. So answer all the 4 questions. What is the correct one in 1, 2, 3 and 4? Each one has their own option correct.
We have to give answer one by one or simultaneously.
Yeah, I mean like one by one. So one has ABCD one option correct. For 2, similarly in ABCD there's one option correct. For 3 and 4 also same. You just pick the correct option for each of the question.
One B.
Yeah, just let's wait for everyone. Yeah, I think they've seen some answers. Yeah, Gayatri has. So I think not Gayatri. Shruti has correctly answered. It's all B's basically. So all the questions, the correct answers are B. So let's discuss it one by one. So before going that, LSTM and GRUs are two different types of RNNs. I think everyone is aware. So let's discuss each of the differences. Number of gates. Number of gates basically is like, for example, in the previous case, these are 3 gates, right, which help a particular LSTM cell to recall certain memory or control certain memory, how it should be updated and all. So those we call it as gates. So LSTM in the like we see in the previous question has three gates. That is correct, which is option B and option D. Whereas GRUs are a slightly smaller version than LSTMs, and they have only two gates. So that is why option B is correct. LSTM has three gates. GRU have two gates. Now let's come to the memory cell concept itself. So in LSTMs, you have a separate memory cell. So if you look at the equation, this equation C, right? CT bar, that is treated like a memory. It is having, it is called as also context. So it is basically having the memory of previous, and when it goes to the next hidden state, that will continue the memory from the previous hidden state. So this memory concept is explicitly there in CT equation, which is in LSTM. So LSTM have a separate memory cell, that is true. Whereas in GRU, you don't have a explicit memory cell, but the update and the reset gate, which is there in GRU, they combine the memory into hidden state. So there is more implicit memory concept in GRUs with the two gates itself. So whereas LSTM have a separate explicit memory component. So B is the correct answer. Let's come to the gating mechanisms. It's just naming the gates. Previously, we saw that LSTM has three gates and GRU has two gates. What are the three gates of LSTM? It's input gate, forget gate, and output gate. And for GRU, the names of the gate are update and reset. So this is a very straightforward terminology only. So the option B is correct. Then comes to the complexity. Now, obviously, the gates are lesser, and each gate come with their own matrix multiplication and matrix vector multiplication and summation, right? So obviously, lesser the gates, lesser the computation. So it is clear that GRU are less computationally expensive than LSTMs because they have fewer gates. So if you just know the gates concept and the memory concepts, all of them can easily be answered. So I hope this is clear. I'll just pause for a second. Any doubts in any of the questions? Okay, great. If there are no questions, let's move on. So now let's look at the vanishing and exploding problem again. So these are the two equations. Your hidden state follows the particular equation, and using that hidden state, you get your output yt for that time step. So in the given these two equations, which matrix do you think is responsible for the exploding or vanishing gradient? So there are three matrices, right? WH, WI, and UH. Out of these three matrices, which do you think is responsible for vanishing or exploding gradient?
Blue matrix.
No, it's not W. Answer, I think again, someone correctly answered it. It's a UH matrix. So, because if you think about it, what is UH doing? UH is multiplying with the previous hidden state. So, what did I say about vanishing or exploding? It is the problem happens when you keep on multiplying over from the previous time steps to previous layers, right? From the lastmost layer to the firstmost layer. So, what is that matrix that keep on multiplying with these gradients? That is UH value. So, this is that matrix that keeps on multiplying with the previous time steps, and which can cause the vanishing or exploding gradient. So the correct answer is UH matrix. Whereas WH and WA, they're not multiplying concurrently, right? They're not having this concurrent multiplication with previous time steps. So they don't cause any exploding gradients. So I hope this is clear. Any doubts in this? Okay. Let's move on a bit more in depth to about the backpropagation itself and the exploding gradients. So previously we said that UH causes the exploding or vanishing gradient. Now I'm giving you a scenario where UH has an eigenvalue greater than 1. What potential issue does this cause during training? These are the four options. There's also justification for all these problems. What does the problem mean is written along with the option, which there's only one correct answer. Select the one. Rupesh, there's only one correct answer, not yeah. I think
Answer is true.
yes, yes, yeah, correct. A lot of people have answered in the chat. Answer is two. So, but let me just quickly explain also for people who are not able to figure it out. So, what does eigenvalues do? When a matrix and vector is multiplied and the matrix has eigenvalue greater than 1, it simply means that when it multiplies with that vector value will keep on increasing. That is a very simple way to think about eigenvalues. So, given a matrix which has greater than 1 eigenvalues, when you multiply that with a vector, that vector will get expanded. Similarly, the opposite, if it's lesser than one eigenvalue, that vector after getting multiplied will shrink in size. So if you understood that, we previously said that UH is nothing but the factor that causes exploding and vanishing gradients. Now, if UH has eigenvalue greater than 1, it means that the gradients which keep on multiplying with UH, they keep on increasing and finally explode beyond a point. So that is why the option 2 is correct, exploding gradient. Okay. So, is everything clear in all the questions? Because I think these are the numerical or MCQ problems which you wanted to discuss. If this is clear, I'll move on to the coding component of today's session. Okay. If there are no questions, let me move on to the code. Okay. So today we will discuss three different networks. Recurrent neural network first we'll discuss, and then we will discuss the how to code the LSTMs and GRUs. So as usual, you don't have to worry about writing all of them from scratch. PyTorch has it very nicely abstracted, and you just have to call RNN module or LSTM or GRU module. But what is needed is the idea of how do you pre-process or do post-processing on these data sets which you get. So that is very critical. So that's what we'll look into today. But the neural network creation and all, it is very similar to how do you create it in your CNN architectures. Okay. So as usual, first we import necessary libraries. I think by this point you all are familiar with all these Torch, the neural network module in Torch, and NumPy as a library. So after that, we look at a simple example first about how do you do pre-processing of text. Let's look at this text. Text equals to, hey, how are you? There are three sentences basically. Hey, how are you? Good, I'm fine. Have a nice day. Now, first you need to identify all the unique characters in these sentences. So you combine all the sentences together and you identify the unique. This is that join and extract the unique characters that will be done by this set. Set is an operator that is inherent to Python. Set basically identifies all the unique elements in a particular given a list or values or what. So then you identify all the unique characters with the set operator. Next, you convert these values to an integer. So int to character is converting integers to characters. Characters to int is the opposite. Convert characters to integers. So why do we need to do this? As you all are aware, the computers don't understand human language. They understand simple numbers. So that is why you need to convert every character into a number. So if you see below, these are the unique characters. There are 15 unique, there is I think 17 unique characters from these three sentences, and each character has been given a number. I is 0, A is 1, H is 2, W is 3. Now, what is the longest string? String is nothing but the sentence. What is the longest string that has the most character? The longest string has 15 characters. So, out of all these 17 unique characters, there is one string in your given three examples which has 15 of these unique characters. So this is just an example of how you convert text to numbers. Now let's look at it. So one other thing you need to keep in mind, just like you do padding in images, right? So why do we do padding in images? To make sure that your convolution after convolution operation, the size remains same. In this case, you do padding for a slightly different reason. Why do we do this? Because each sentence might be of a different length. But when you're processing them, it means when you're combining them as batches or as one big input to the neural network, they have to all be in the same size. Otherwise, the input to the neural network will be of different sizes, which the neural network can't handle. So because of that reason, you do padding. So again, very simple here. Over there in CNNs, we by default use zero padding. Here you add a white space. That is just a space bar, right? Just this white space you add for sentences that are less than the maximum length of this of a sentence in that examples. So I hope this is also clear. And then
How computer operates this white space as?
also there are some unique numbers to certain special characters like white space or for that reason your next line. All these, like next line is nothing but \n in terms of coding language. So all these are called as special characters. They are already inbuilt. Each language has given some numbers to these special characters.
Okay.
Yeah. Then let's see about how you can. This is just a small operation where you want to remove the last character, where you can just get the text in this for loop. You go across each of the text, and then you just do -1, which removes the last character. And if you want to remove the first character, you just index it from the starting. So this is simple indexing of your normal list, right? So this is what we want to show, that every text inherently becomes a list, and that list, each value is nothing but a character in that text. So that is what this is showing. So you can remove either the last one by just indexing up till there. Oh, this is just an operation. Don't worry about it. This is just to show that it treats it as a thing. So it's sometimes good.
This is for the trimming of the sentence.
No, no. This is will show you the training comes in the bot. Training is not yet started. This I'm just showing the different type of
No, no, I
features.
am not talking about the training. I am talking about trimming. Trim.
Trimming,
the-
yes, yes, yes. These are just trimming of the characters. You trim it either from the start or you trim it either from the last. Okay. Then you convert all of the characters into integers using this char to int, and then now you do one-hot encoding. So one-hot encoding is very important. Previously, if you remember, we did one-hot encoding in images, right? For images, you have class labels. Like class labels go from 0 to 10. What does one-hot encoding do? If you have, let's just say, 10 characters, then each class will be a value in. You first create a vector of 10, and then you put one corresponding to that particular class label. So a simple y vector, which was previously 10 cross 1, let's say, now after one-hot encoding, it will become 10 cross 10. So each class will have a 10 size vector, and you put a 1 corresponding to that particular class label. Wherever 1 will be at the first position, 3 will be at the third position in that vector. You put 1, remaining all will be zeros. So that is a standard one-hot encoding. So you do the same thing with your text also over here. So how do we do it with the text? So you first create all the zero vectors, like I said, zero of this size, batch size, we need to know, sequence, and the dictionary size. Sequence length is basically how many characters are there in your particular sequence, right? That is the sequence length. Dictionary size is what are all the unique characters, like all the unique labels that are possible, classes that are possible. That will be your dictionary size. So you first create this vector of all zeros, and then you replace the zero at the relevant character with one to represent that character. Just like if class 1 was there, at first index you put 1, sequence length, you travel across the sequence length, and at each character you see what is that number corresponding to that character, and in that entire dictionary you put a 1 at that particular position. Just standard encoding size, which we one-hot encoding, which we do. I'll just quickly pause. Is this clear, right? I think this is there any question one-hot encoding? Okay. Then let's move ahead. So this is what your input sequence gets the shape. Your input sequence is now going from 3, 14, 17, which is nothing but batch size, sequence length, and one-hot encoding size, which is the dictionary size. Now you convert these input sequences and target sequences to tensors, basically. That is how you do torch from NumPy and torch.tensor. Then you first check if you have GPUs. This again, these are standard practices. How do you check the GPU? You use the CUDA dot is available. So this will tell you, like gives you a boolean value whether as a true or a false. So if there is GPU, you'll get your true value, and that's what you do. If there is, if is CUDA is true, you set a variable device which is which is pointing towards the CUDA device. Otherwise, you set a variable device which points to CPU device. Now let's come to the model definition itself. So what is the model? Here we'll use a simple RNN. Next we'll talk about LSTM and GRU. First we'll discuss about a simple RNN. Like always, your neural network model should basically be a class, and that class should inherit a parent class called as nn.module. Very important, this particular line. Please don't forget, whenever you're creating your neural network class, always inherit the parent class nn.module, which will basically tell the neural network, which will basically tell PyTorch that this particular class is of the type neural network class. And then, like I always say, there are two important functions that you have to definitely create for every neural network. You can create more than two, that depends on your neural network definition. But the standard two which have to always be defined is these two functions: init function and the forward function. Init function basically helps you in creating a bunch of global variables which you will be using in your forward function. Like, what can be the global variables? You can create an instance of this nn.rnn class, or you can create global variables which define how many number of hidden dimensions should be there or number of layers that should be there. You also create a global variable that will create an instance of linear class, which will the fully connected layer. So bunch of these global variables are created in init function. Now, as when the model is called, right, when you create an instance of the model, the init function automatically gets executed and all these global variables are created. Next, in the forward function, this particular function is executed when you send some input data to the model. When you're training, right, you remember how do you send? You just write your model in brackets, you send the input data. So when you send that, write that command, this particular forward function then gets executed. And what does the forward function do? The forward function basically defines how should the data travel from one layer to the other layer. So starting from your input layer, you go first to the hidden layer, and then you go to the RNN, then you go to the fully connected, and then you get the output. So here, what is this hidden layer? It is nothing but zeros, which we define in the bottom. This init hidden layer is again defined. It is nothing but a bunch of zero values. So maybe let's. Why do you think we should start off with zero values? Any guesses? Why do we hidden states start off with zero values, or can it be any value? Any guesses? Okay. So basically, like, what does the RNN ideology is? RNN's ideology is you are dependent on your previous time step. But what do we do at the first time step, right? There is no dependency. That is where you're starting. So it is always good to start with zero, because then you're telling the model that there's nothing to depend on, or there's nothing to look from the previous time step. If you have some other values, then unnecessarily you're complicating and telling that this is not the starting point. It means that there is some other dependencies happening, which is not, that is your starting of the sentence. I hope that is clear. So that is what you're initializing your hidden states with all zero values, and that is basically stored in this variable hidden. Now you send your data to the RNN class object, sorry, RNN object, which takes the input and the hidden value, and inside this your all the operations happen. You're calculating of your next time step and your output and all. So that is what you get output from this particular self.rnn. You get your output for that particular time step and also the hidden state for the next time step. Then you send this to the fully connected layer, and then this fully connected layer will basically map these outputs. You have your certain dimensions. From your hidden dimension layer, you go to the output size, which is usually your number of classes, in this case your dictionary size. So that is what this fully connected layer will map your hidden output of the RNA to your class values, and you finally return your output and the hidden state. So in this way, you create a simple RNN network. It's not very complicated. So next we'll see how the training of this is done. So here I'm first instantiating the model with certain hyperparameters, like what should be the hyperparameters, like what is the dictionary size, or that is the input size, what is the output size, then what is the hidden dimensions that I want, and number of layers. We created a very small one layer RNN. You can always, like I said, play around with these values. The more you play around, the more you can see how the architecture, like how the model learns, or what type of representations are being learned by this RNNs, or what do RNNs do. So once you create an instance of this model, you send it to the device, which is your GPU device. Then you define the epochs, how many epochs you want to run this. You run it for 100 epochs. You define your learning rate. Again, these might not be the best values. It depends on your data set. You always need to play around with them and decide. Okay, then we define two. Yeah, is there a question?
What is hidden dimension here? Can you please explain again?
Yeah, so this hidden dimension, we are sending it to the RNN. So RNNs have hidden state dimension, right? It has a hidden state and the dimension for that. That is this basically.
Hidden state. Isn't it automatically inferred from the input dimension? Or?
No, it's not necessary. No, not necessary, right? So your hidden dimensions can be a smaller size than the input. It's not always a certain ratio or something. It's not directly inferred. You need to specify. You can have a ratio based also, but it's not standard practice.
Okay, got it. Thank you.
Yeah. Okay. And then let's come to the loss and the optimization.
Sorry to interrupt you.
Yeah.
Even in a basic RNN, the hidden dimensions will be lower to the input or same as the input.
So it's again this is again one thing which you have to play around and check. It's not it's not necessary. It's all like, or it's compulsory that it should always be smaller. Sometimes smaller works better because you want to go from higher dimension. Input is usually higher dimensions, right? You want to go from higher dimensions to lower dimensions. But sometimes you have small dimensions as input, then you want to first project it into bigger spaces. So it depends on your input use case. So imagine it to be like your convolution operation itself. Sometimes you use padding, right? It means that in the after input, when you use padding, you're not reducing the size. You're still maintaining that size. After some time, you're reducing the size of that convolutions. So why are we doing that? To maintain the same dimensions, to extract information in a good way. So it depends on your use cases, actually. It's clear. So next we define the loss and the optimizer. So here we using simple cross entropy loss. Again, it's defined very well in your NN class, NN module, NN dot cross entropy loss. Then you have something called as optim module in Torch, torch dot optim, which has a bunch of optimizers readily available. Adam optimizer, you have your standard gradient descent, stochastic gradient descent, then RMS prop. All these optimizers are available in this particular optim library. Once you define them, then you need to write a small for loop, which will basically train your model. So what is the for loop? For epoch in range of epochs, which is 100 times it's going to run. So it's the same 5 steps which you always follow for training a model. What are the 5 steps? First is you zero out your gradients. You can write this either on the start or on the bottom, but always have it in the for loop. First you zero out the gradients, then you send your input, basically do the forward pass to the model that is at this point, and then you send your output and calculate the loss. Your basically output and target is being sent to device. That can be sent in the before step itself, but you can do it wherever you want. But important step is you send your output and target to the loss function. So once the loss is calculated, then you do loss dot backwards, and then you do optimizer dot step. So loss dot backwards basically calculates the gradients and all the partial derivatives. Optimizer dot step is where you update the weights. So these two steps does the back propagation. Forward pass is done by this model of input sequence, and optimizes the zero gradient is very important. It basically clears any existing or previous gradients. So I think this is a standard training loop, which by now you must be aware of. We've been using it same for the CNN also. Okay. Once you train, now what is important is this post processing, which is this predict function. So let's look at the sample function first. The sample is basically calling the predict function. So after you train the model, so let's say now you want to generate 15 characters, which the starting prompt as good. So I need to get something like this: good, I am fine. So I'm giving the prompt or the input as good. I need in total 15 characters as the output. So what is this called as? This is called as character level modeling, which we call, where your model takes in the input characters and outputs character by character depending on how many or what is the output length you want. So this sample function, let's look at it first. Sample function takes three things as input: your model, your final output length that you want, and the prompt, input prompt or the starting word, which is by default hai, but we are giving the word good, so it is over it. Now you first set your model to eval phase, then you first lowercase all your characters. If there are any capital characters, it will go into lower. Then you create, you break this entire string of initial characters, and then sorry, this entire string of initial word into characters. That is this particular char's variable doing. This is taking each character in the initial word, and then you identify, because obviously you want total output length to be 15, right? So initially your word will have certain length, so that you're subtracting from your output length to know what should be the total extra characters that you need to predict, more extra characters. That is what size variable is keeping track of. Then now you run a for loop across a for loop for this size, where each time you call the model, you predict the model to give the next character, and how many times you do it depending on this size value. So here you have four, right? One, two, three, four. Good has four characters. You want in total 15. So size value is 11. So now you call model predictions 11 times, and it predicts 11 different characters, and all of them are appended into this characters variable, sorry, in this characters list, and that is what is sorry, that is what is returned, which is good, I am fine. Now let's look at the predict function. What does the predict function do? It takes two things as input: model and the characters. Characters list is basically what are all the characters that have been predicted till now, including the starting initial word, which is good. So let's look at the predict function. So first, the character is converted from characters into integers using the char to int format, which we discussed. Then you do your one hot encoding of this particular characters which you got. Now you send them, you create tensors and you send them to devices, and then you send this character into the model. This is where you're doing your forward pass, and this that forward function takes this character as input, goes through your RNN, then goes to your fully connected layer, and then returns the output of the next character that should become. So it returns a vector, and out of that vector, you pick the one which has the highest softmax. Which the last character, it has bunch of 15 different 17 different possibilities. You pick the one which has the highest probability. So that is what this softmax value is basically saying. Softmax, sorry, not softmax. First you're converting into probabilities, and then this torch.max is where you're picking the uh, maximum character probability value. That particular index is what is written, and that is what is stored in this characters list, which is what is returned finally. So I hope this entire flow is clear of how you are inferencing and doing post processing. Any doubt in the post processing, the predict function or the sample function? So the main aim is not text for this course. I understand it's a vision based course, but it's important to understand these models because you use these models for video based processing. So, and in fact, if you understand this, it will be easier also to understand how the sequential modeling is done, because text are the most easiest form of data to understand sequential learning. So your attention transformers, all of them it'll be easier for you to understand if you're understanding how these processing input pre and post processing happens. So any questions or anything that is not clear in the sample and predict function?
So can you please go through the predict function again?
Yes, sure. So you understood the sample function?
Yes, I do.
Okay. So in sample, let's go. So first, good will come. The 4 characters will be there in the characters list. Okay. Now, in the first time when this loop runs, the predict function gets the model and a list of all these 4 characters. Now, if you look at the predict function, you first convert each character into an integer. The GOOD is converted into numbers. Then you one not encode all these each number, each character basically, which has a number. Then you just convert into tensor and send it to the GPU device. This is needed because your model is on GPU.
So we
And
do
mod-
we do one hot encoding using the same vocabulary we have defined earlier for training, right?
Yes. One hot encoding follows the same. That's why the dictionary is written, right? It's the same dictionary that needs to be followed.
Actually, it's one of how encoding does. Like, can we use another encoding in PyTorch?
I think, see, one hot encoding, like I said, right? You basically convert everything into a string of 0 and 1 and give convert your integer classes like between which is 0 to 10 into a bunch of vectors which defines of the class size and between 0 to 1. So if you're asking is one hot encoding the only way possible, obviously not. There have been some other methods, but I'm not sure the names.
Even
But-
even these days, some people use tokenizers.
Uh,
Like,
Yes, tokenizers also, that is a different type of pre-processing. That is also possible. That is more somehow they also use some type of one-hot encoding even in tokenizers, but one-hot encoding is very popular. That is the most popular ones which we use for most of the images, especially for text. Like someone pointed out, tokenizers are also possible.
Okay.
So once you create that, you send that as an input. Sorry, isn't it, Mishka?
No question, sir.
Yeah.
Please.
Yeah.
Go.
So that input GOOD one not encoded values is sent as an input to model, and then the model. If you look at the definition of the model, in this forward function is called now. Now, what does a forward function do? It sends. It first creates a hidden state. Then that hidden state and RNN is sent as that's X, right? GOOD is sent as an input along with the 0 initialized hidden state, and the RNN computes using the 2 equations. Basically, it computes that entire length, and then it outputs the y value, which is a vector of values. It is what is the vector size is again depending on your dictionary. It's 17 characters, so it's output a 17 vector with different values in between, which we call the logits. So if you come to the predict function, so output -1, we're just looking at the last one because the output will be predicting for each of these. G, it will predict something. O, it will predict something. Again, second O, it will predict something. Again, D. But we don't want the outputs for G because we already know after G, O will come, right? So we ignore all of them. We only look at the last output, which is basically after D, right? Which is the output that is coming. That is what we're interested in because that will help us in predicting the next character. So that is why here we do out of -1, the last one we take. Now these are logits. Logits can be any value between -infinity to +infinity. We convert them into a probability using softmax, and then this is again a vector of your dictionary size, which is 17. In these 17 different values, which is the maximum value, you take that particular index because that index corresponds to that particular character, right? So you take that particular index and you return it. Before returning, you again convert from integer to character, which is the same function which we wrote on the top. That will convert that particular character integer index into a character, and that character is what is returned, which will get appended to this chars list. And you repeat this process 10 more times, and finally you get this as the output. Good, I am fine. Is this
Aren't we, it's clear, but aren't we inputting the last generated output character again to predict the next character?
Yeah, we are always not just last. Yeah, not just last. We are taking everything. So, for example, after good, your prediction is a space. Now,
Okay.
in the next iteration, you take space and all the good together, and again predict I. So always the context is increasing. The input context keeps on increasing. If you look the characters, right, it's keep on appending. That is what is going as input.
Yes, yes. Got it, sir. Thank you.
Okay. Any other questions anyone has on this?
These RNN maintain the sentence level dictionaries or complete dictionaries.
What is sentence level? There's only one dictionary in this, which is character.
There are 17 character in all the three sentences. Okay. Then the system maintains the 17 character.
That's
Now we can take the example of Google, which have the millions of words. Now Google maintains, in case of RN, thousand or million level dictionary or each sentence level dictionary.
So that's a different task you're talking about. So there are a bunch of different tasks. So first,
Okay.
what we are talking about here is character level modeling. So here, your character is a each unique character will be one element in the dictionary. Then there is word level modeling also, where you predict multiple words. No one does usually character level these days. People do mostly word level, where you predict multiple words. In there, which you're talking about tokenizers, right? That will come into picture, where each token is either not completely a word, it's a partial word or a type of a word. So words will become unique characters over there. Okay, so that is clear. Let's move ahead to LSTMs and GRUs. So here we now look at a different problem. So here we have something called as the energy based problem. So energy based problem, what basically says is, over a period of time, this is the date time, it has month, year, and also the time. Over a period of time, the energy consumption, I think, of a grid, of a particular grid is given in this data. You have to basically model this and predict it in the next time, how much what is the expected amount of energy consumption. So maybe you can look into this data if you're interested. So it has a bunch of different CSV files. You can look into all of these and see what exactly do they mean. But as far as I remember, it is basically energy consumption. But that is not important. You're just modeling it. We'll just look at it. So first thing first, you read your CSV files using Pandas. Pandas is a library which is very good for reading your CSV files. And so the command is to read CSV. You give your particular CSV file path, and then this dot head basically prints the first 5 values. So it is good to visualize your data always. So dot head basically visualizes the first 5 rows and all the columns. So there are 2 columns in this, the date time, and the second column is your energy consumption column. Now, before sending the data, there is a bunch of things pre-processing that you'll have to do. So let's look at those. Firstly, there are all these files which you want to combine and send as the input. So you create all the files in this directory list, where one by one you open the CSV file and then do some pre-processing, and then calculate the train part and the test part from that file, and then you append it to the mean, train, and test. That is what this train and test X is there. Similar, so what are the pre-processing steps? Let's look. So we first convert those date, time, and month and year into their respective columns. So you just do, you look at the text, which is this text, right? You look at this entire text, and then you split according to there. So all these first splits are done based on years, and you create a column for years, you create a column for month, you create a column for date, you create a column for time. And this is what is happening. So you create 4 columns: hour, day of the week, month, and day of the year. So this basically, you can look at the how it is applied: dot hour, dot day of the week, dot month, and dot day of the year. These are all existing values which are present in your particular CSV file. So we are not doing much over here, we're just extracting those informations. Okay, so once you parse the data and you create those, this is standard parsing of pandas. This has nothing to do with anything of PyTorch or something. We look at the scaling, which is now important. What does scaling do? Like I always say, scale the data, because that will bring every feature or input attribute into the same scale, either 0 or 1 or whatever scale you want to bring, but have a common scale, because that will help in your training process. it'll speed up the optimization process. If there are of different scales, your model sometimes won't even converge. Forget converging fast, it won't even converge sometimes. So for that, in this particular case, we use a different scalar, which is called as min-max scalar. Basically, it scales taking the maximum value. You take the current value minus the minimum value divided by maximum minus minimum value. That is what this min-max scalar do. And then you transform all your existing attributes, all these hour, day of the week, month, and day of the year, into this min-max scalar. So all your columns are now scaled between 0 and 1, or yeah, it's scaled between 0 and 1. Once you do that, then there is something called as label scalar. Now, why do we need this label scalar? Because if you look at the outputs are between like it's like kind of 0 to infinite value. It's like any real value, right? It's not between 0 and 1. Whereas your model always predicts between 0 and 1. So the predictions from your model 0 and 1 needs to be multiplied with a certain scaling factor to get back into these scale values. So to get that factor, you need to identify what is that scaling factor that I need to get from this particular last column. So that is what we are keeping in label scale. So label scale dot fit basically looks at the column, the label column, and tries to fit using this min-max classifier. So once it fits the label column with this min-max classifier, you can use this scalar to multiply it with your predictions between 0 and 1, and you'll get the final output, that real value. So this is a bit different from your standard CNNs. This you never do, but for usually these type of problems or data sets, it's good to have these label scalars. Okay. Now, once you create those label scalars, next thing what you need to create is look back period. So what these look back period says. So as I said, previously we had a sentence. So we know key sentence comes in sequential manner, right? So you are looking like for example at this. In this example, good, I'm fine. When I'm at this I'm looking at everything that is coming before that. So the context period or the look back period is everything that is coming before it. Similarly for A, everything before A is the look back period. But in this particular time, there's nothing like that. We don't see very clearly what should be it. So it could be everything that is coming before it. That is one possibility. Or you can take a certain set of window. So that is what we are defining over here. So we say 90 samples or 90 periods is what your look back time will be. So at a particular row, all the 90 values before that particular row will be your hidden values or look back values. So that is what you create your inputs and labels to have those look back values, which will become your hidden states input basically. Now, once you create those look back values in this for loop, so first you create bunch of zeros and then you add the look back value based on the data of the previous layer. You add that value into the look back of this particular input state. So now you split the existing data into your train and test split. So this is again standard train and test split. Test portion is 10% of your entire data set, and the train parts also you're creating. Train parts is everything that is not a test. So once you do this, you're basically now running across. So you're now going across this for loop across every file, creating a train test split, appending all the train values into your final train test, appending all the test values into your final test split. So this is what this final test file and train file will do. So is this clear? The pre-processing of look back and label scalar and everything. Any doubts in this? Great. If there are no doubts, let's move ahead. So once you create your data, now again everything falls back to your standard creating of data sets, data loaders, and everything. So first, let's look at it. We are creating a batch size of 1024, which is a very huge batch size. It means that this is because again we are combining from multiple CSV files, right? So we have a very big data set. So that's why you're having a big data batch size. So maybe a question. Usually we don't use such big batch size, but how is it possible that our memory is fine when we use a batch size of 1024 in this case? It's a very simple answer. Any guesses?
Because we have to go to 90 samples behind the current sample. That's why we have to take the sample size more than 100.
Oh, no, but the batch size is 1024, not 124. 100, it's 1000. So this is nothing to do with the look back side, because look back is done for every sample. The batch size is picking number of samples. Whatever samples you pick, all of them will have the certain look back. This has nothing, don't confuse the batch size with the look back period. Look back period is just the hidden state which is going to be attached to every sample. The question here is, why, how many samples should I pick in a batch? It basically is decided on the memory capacity. That is why previously we only picked 64, 32, or 128. But now I'm able to pick one or two samples at a time and load it in the memory. But why is it possible this time and not, it was not possible previously? What is the change that has happened?
Because the matrix size is so small.
Exactly. So basically, previously we had images, right? Previously we had images which were of the size 32 cross 32 or 22, 224, 224. All of them are very big values. So that is why loading them is hard. Whereas loading these are very simple values, right? These are just these numbers. It doesn't take much of a space to load these numbers. So that is why we are okay with loading batch size, bigger batch size. So I just wanted to bring this point because even somehow in the future, our GPU memory size increases. Don't stick with batch size 32, or even currently, if your memory size, if you have a GPU with a good memory, don't stick with 32 batch size, because as we know, convergence happens better with higher batch size up to a certain extent. It's not like it's always more and more better with more and more batch size, but it's better that if you have a bigger batch size, convergence can be better. So don't just limit because you thought that 32 is a standard practice. Okay, let's go ahead.
Batch size, the value of raised to power something, anything. So why is it necessary? Why that we take the batch size for the 2 raised to power of some number? Why not random pickup of batch size?
No, you can pick random also. It's not necessary. It's a standard practice. Like I said, these two raised to the power, right? Two, like 32, starts off from 8 actually. 8, 30, 16, 32, 64, 128, 256. This is a standard practice. But that being said, it's not, I've used batch size which are also 40, 41, 52. It's just very good sequence to have these two raised to the power, and that's a standard practice. But it has nothing that it's a limitation.
Okay.
Yeah, it's just a value. You can put any values and check. That's not okay. Then you first create your dataset, tensor dataset from the previously created NumPy train X and train Y and test X and text Y. You first create your tensor dataset for train. This is nothing but you you first convert your NumPy to a tensor using torch.from NumPy, both X and Y values. And then after you creating your dataset, you then send it to the data loader. The data loader is where you create your batches, shuffle your data, and also, okay, maybe I'll ask this question. I don't think I've asked till now. What is this drop last equal to true? Why is it needed? Any guesses? What is this parameter argument in data loaders? Drop last equals to true, and why is it needed? So basically, like I said, I think someone also asked this question. The 2 to the power, right? You can think of both of them kind of connected. Or so when you have a data set which is not easily split into equal number of batches. Like for example, what I mean is, if I take 2 as the batch size, okay, and if I have a data set of size 10, so how many batches will be created? 5, but all of 5 are equally 2. But if I have a data set of size 9, now the first 4 batches will have 2 samples, but the last batch will have only 1 sample. So that is problematic because then your input is not even, right? So that will cause your model to fail, your operations to fail, when especially you're converting them into calculating the loss or certain other operations, those will fail over there. So that is why this drop last says that whenever you have these what do you say, imbalance in this last batch which is not equal to the batch size, you just drop that entire batch. So I hope that is clear. So it's a very simple thing. Just keep it false and also check, keep it true and also check. You'll just see different values. So this are some different.
But why we not use at the time of image data sets?
No, we do use implicit default, by default it is true. Yeah, I think by default it is true. Otherwise, maybe they made it right now as false, but it was by default to be true. You always drop it. So your batch size then goes on to the same thing. So you can have a batch size to a number where you can easily split your data set. Otherwise, you can just keep number to the power 2 and you can just use drop last equal to. Okay. Once you create your train loaders, data loaders, then you again, this is standard GPU availability. And I think by this point you all are aware. Then we'll go to creation of these two networks, GRU network, LSTM network. So we create two networks, but we only use one at a time. In this, we'll show you the LSTM. You can similarly just replace LSTM and call GRU instead of that. It'll work the same way. So let's look at the network itself. It's very similar to your RNN network, what we created. We are having the first you create a class inheriting the parent class NN.module. You create two important functions, init function and forward. The third function is specific to this particular RNNs, which is initialize your hidden state, which is nothing but all your here the initialization of hidden state is slightly different. It's not all zeros. So this particular hidden state is coming from the data of the parameters itself, which is a slightly different version than your RNNs, because here GRU networks hidden states kind of depend on the previous hidden states. So that is why it's slightly different. I'll confirm this once again by exactly not zero, and I'll let you know in the next session. But it's a slightly bit different from your typical RNNs when you initialize it with zero. But the other two things remains the same. Your init function, you define all your standard global variables, how many hidden dimensions, how many layers. You instead of your nn.rnn which you used previously, we use nn.gru, and then we use your fully connected layer, and then you use your ReLU activation. In the forward function, you just call them. So in our forward function, you call self.gru, the x and the h values which go, and then you send it output of the GRU to the fully connected and you get your output. Similarly for LSTMs also, you do the same thing. LSTMs here, you define your init function, forward function, and initialize the hidden state. And then you create your same global variables. Instead of nn.gru, you call nn.lstm over here. You have your same linear and ReLU layer. The forward function also works the same way. Everything is same, only difference is replacing the GRU with LSTM. Now let's come to the train methodology itself. So here, like I said, you can you can use the same training function for both GRU and LSTM. Based on this condition, you pick your model. So in this case, by default, it's GRU. So you just go to the GRU and you create an instance of the model of the GRU. And then you also create your loss, which is your mean square loss over here. Why? Okay, again, another question. Why mean square loss? Why not other losses, cross entropy?
Because we are using the numerical data.
Right, it's a regression problem basically. So it's a mean square loss error. Previously, we used a character level modeling, and there were classes for those characters, right, in the dictionary. That's why it was a cross entropy. Then we create your optimizer, which is your Adam optimizer, and then you start your for loop. Here you have your two for loops, one which goes across the epochs, which you define, and then one which goes across the all the batches in your data load. So once all the batches is seen by the model, then you finish one epoch, and then you repeat that entire two loop process for total number of epochs. So here you first initialize your model with the initial hidden state, and then this h is then send it to the here you are sending the concept.
Is shuffle is equal to true impact on this model or not?
Yeah, shuffle. You mean the data loaders, right? Data
Yeah.
loader shuffle. Yeah. Always shuffle equals to 2 will impact.
Because the current
Oh,
value
okay.
is
So
90 and 90 previous value, then
see, you're shuffling. No, you're shuffling across batches which has samples, which is like in a batch you have 32 samples. Each sample has 90. When you do shuffle true, you're not shuffling the 90 values. You're shuffling these samples. But when you pick a sample, you have the memory of that 90 saved with that particular sample.
but
There's a
but each sample depends on its previous
No,
continuous
okay.
20 samples.
Yeah, but that we've already stored over here, right? Inputs dot data look back. That variable is taken care of. So
Yeah,
the
you are right, but we have not indexed anything.
no, we
Okay.
have the shape. Look at the shape. The shape over here of the input is not 2 dimensions. It is 3 dimensions.
Okay.
Yeah. So you're keeping a track of it. It's not that on the fly it is happening. You collect the data in such a way you create your input to have these dimensions. Is that clear?
Yes. Yes.
Yes. So okay, good. Thank you for pointing it out. So this is the shuffle equal to true won't affect this. It will still shuffle the values in the batches. Okay, what was I? Yeah. So here we go into the inner loop, which is the train loader loop, and then you initialize the values of the h values which we got from the model initialization of GRE or LST, and then you send those x as an input along with the hidden state, and then you get your output. And here, as usual, first you need to do zero gradient. Sorry. Then you do your forward pass. Then you calculate the loss, and after you calculate the loss, the two other steps are your loss dot backwards and optimizer dot step. So these again 5 steps are standard across any neural network. So zero in out gradients, do a forward pass, calculate the loss, do a loss dot backwards, and then do the update step, which is optimizer dot step. And other parts is just printing statements, like after how many steps you want to print to show what is the loss, or after each epoch you want to print what is the total loss in that epoch and how much time has passed. These are just standard print statements, which is not nothing to do with the training. You can print it for you to keep a track of it, or you can just store the values and plot it like we did for the last sessions. Okay. So once you do that, evaluate function again. Here now we'll use those label scalars. If you remember, label scalars. I'll tell you where how exactly we're using. But before that, evaluate function takes your model, your test, and your label scalars as input. First, you change the phase of the model to model.eval, and then you uh, go across all the test samples in this for loop. And first you convert the samples into tensors, and then you send those tensors as an input. Here you send the previous hidden states also, initialize the hidden states for each input, because the 90 look back is also there for each test sample, right? Then you do a forward pass on that input. Then once you get the output, here you do the inverse transform. Inverse transform basically, so fit transform converts your original values to your label scale 0 to 1. Inverse transform does the opposite. It takes the 0 1 and multiplies with that factor so that you get your output in a real number. So that's what you do, inverse transform for your outputs along with your targets. Then you know how much is your evaluation. That here you call with your once again. Here your loss is mean absolute value, MAPE. This is a metric. This metric basically you print the value. So it's not a simple accuracy metric. This is the different metric over here, which is the absolute error kind of a thing. Uh, Maximum a posterior error. So we can call it the absolute error. So that is what is calculated for all of the test samples. So the important thing about what I want you to guys take here is the inverse transform. So make sure you always convert back to from 0 to 1 to the original scale. And then after that, it's just calling those functions and you just train. And then you evaluate, and this is the final evaluation metric for this particular regression task. Yeah, so this is what I wanted to discuss in today's coding. So you can just do the same thing for LSTM also. You can just replace the model type LSTM. And we just commented, you can just run these two commands, you'll get the same thing. So this is what I wanted to discuss. Any questions or anything related to any content that we discussed?
While defining LR, what is the LR doing here right now in my model here? In GR?
LR is your learning rate. So LR learning rate, you familiar with the concept? Or?
Yeah, learning rate I know. But what is doing here in my model, that is GRU model?
So LR is used for update of your weights. It has nothing to do with your what is a particular model. It is related to the optimization process, which is your gradient descent algorithm. So if you look at the gradient descent update rule, it says current W is equals to W of previous plus the learning rate alpha value into the gradient. This alpha value is your LR over here. So based on that alpha value, you decide how much you should be confident on the gradient and take a step size for in that direction. Smaller LR takes smaller step sizes, bigger LR takes bigger step sizes. Is that clear?
Yeah, it's
Okay. Any other questions anyone else has? Okay, then if there are no further questions, thank you all for joining. This is what I
Thank you. Thanks to all.